Hello all. Today in this video we are going to see about coupling constant. Okay. So first of all, what is coupling? The word coupling. See here in the previous video we have a discussion about splitting of signals, right? Splitting of signals, that is multiplicity. In that case, what I have told you, see, this will split with the help of neighboring proton, right? This signal, actually we will get two signals for this. This is methyl proton, this is methylene proton, so we will have two signals. So how can you draw the signals? You can draw the signal like this, but you will not get the peak like this. It may have some splitting, right? So it may be quartet, and here it may be triplet, right? See, quartet, and you may have triplet, right? So this is possible. Why? Because the neighboring proton will split the signal, right? Here for this, actually, see the neighboring, how will you calculate the multiplicity? See the neighboring proton, you have 3 protons, hence n plus 1 formula, the answer will be 4, right? 3 protons, n plus 1, 4, which means you will get a multiplicity of 4, right? So it will be in 1:3:3:1. These and all I have told you in the previous video. If you haven't watched that video, then kindly watch that video. Okay. So this is how you have to draw, right? The spectrum. And here it will be 1:2:1 ratio, and it is a triplet. For this, because two neighboring protons are there, right? These two neighboring protons will split the signal into triplet. So this is known as a splitting of signals, spin splitting. Okay, otherwise it is known as spin coupling, because the neighboring proton couples with another neighboring proton, right? This proton couples with this, and this couples with this, right? Hence it is known as coupling, spin coupling. Okay. Now, so coupling are of several types, right? One coupling, J1 coupling, J2 coupling, J3 coupling, J4 coupling. So first of all, what do you mean by coupling? The J1 coupling means this indicates the number of bonds, okay? The number of bonds between two protons, right? See here, in this case, it is only one bond, right? You have only one bond. It is known as J1 coupling, okay? J1 coupling. See, in this case, this number indicates number of intervening bonds, okay? Number of intervening bonds. The number of bonds present between these, okay? See here, in this case, this hydrogen is here and this hydrogen is here. The number of bonds present between these two is 1, 2. Hence it is known as J2 coupling, okay? J2 coupling. See here, in this case there is a proton. It may couple with this proton. The number of bonds, see here, 1, 2, 3. Okay, hence it is known as J3 coupling, right? Similarly, in this case it is 1, 2, 3, 4. This is known as J4 coupling. Okay, these are all the classification of coupling. There may be of J1 coupling, J2 coupling, J3 coupling, or J4 coupling. J4 coupling is otherwise known as W coupling. See here, it is in the shape of W, right? It is in the shape of W. Hence it is known as W coupling or meta coupling, because in case of a ring structure, see here there is a proton, okay? Here there is a proton, and if it couples with this, what is the number of bond? 1, 2, 3. So ortho coupling means J3 coupling, okay? Ortho J3 coupling. But in the meta position, see here, 1, 2, 3, 4, right? I can draw like this. Okay, so this is HA proton, this is HB proton, right? Now the number of intervening bonds between these two is 1, 2, 3, 4, right? Hence it is known as J4 coupling is otherwise known as meta coupling. In ring structure it is meta position. Okay, ortho coupling is J3 coupling, meta coupling is J4 coupling. This is not considered. Okay, actually this coupling is very weak because distance is maximum, right? Maximum in case of meta when compared with ortho. Hence J4 coupling, generally we won't consider J4 coupling due to large distance between these two. So they won't couple that much, right? This is the concept. Okay, these are the details about coupling. Okay, coupling are of 4 types: J1 coupling, J2 coupling, J3 coupling, J4 coupling. Generally we won't consider J4 coupling because of large distance between the two groups, right? This is otherwise known as J4 coupling is otherwise known as W coupling or meta coupling. Okay, J3 coupling in the ring structure it is nothing but ortho coupling. Okay, ortho coupling. And see here, what kind of carbon is this? It is geminal carbon, right? Geminal means, see, if two groups are present on the same carbon, it is known as geminal. Okay, geminal carbon. Hence it is known as geminal coupling. J2 coupling is otherwise known as geminal coupling. Okay, similarly, if two groups are present in the adjacent position, it is known as vicinal. Okay, vicinal carbons. Hence this J3 coupling can be known as vicinal coupling. Okay, vicinal coupling. This is J2 is geminal coupling and J3 is vicinal coupling. Okay, so the overall summary is J2 coupling is geminal coupling, J3 coupling is vicinal coupling, J4 coupling is W coupling or meta coupling. Okay, W coupling or meta coupling, right? And one more thing, this number indicates the number of bonds. Okay, number of bonds, intervening bonds between the two groups that couples. Okay. So now we are moving on to the topic coupling constant, right? Coupling constant. So what do you mean by the term coupling constant? It is nothing but separation of lines of multiplet. Okay, separation of lines of multiplet. If suppose I am having a peak like this, okay, I am having two peaks. So there is a separation between them, right? From the center, from this to this, there is a separation. Okay, the distance between the two peaks, center of the two peaks. Okay, distance between center of the two peaks is known as J, coupling constant, right? Separation of two peaks. Okay, distance between centers of peaks. Okay, centers of peaks is known as coupling constant, right? Coupling constant. So see here, in this case it will be very simple if you see the example. See, in this case it is 3.5, right? This peak chemical shift value of this peak is 3.5 and here it is 3.3. So how will you find out the coupling constant? I told you it is the distance between center of the two peaks, right? Distance between center of the two peaks. Hence this is 3.5 and this is 3.3. So you have to subtract it, right? 3.5 minus 3.3, it is 0.2, right? It is 0.2. This is how you have to find out. But this 3.5 and 3.3 chemical shift values will be in ppm, right? So the answer is also in ppm now. Okay, because always chemical shift values will be measured in parts per million, ppm. Hence, this value, if you subtract these two values, you will get the value in the ppm, right? But coupling constant, the standard unit for coupling constant is hertz. Okay, the standard unit for coupling constant is hertz. So I told you in the previous video itself this formula, ppm is equal to hertz by megahertz. Okay, so if you want to convert this ppm value into hertz, what you have to do? Hertz is equal to ppm into megahertz. Okay, ppm into megahertz. So you can convert this ppm into hertz, okay, by multiplying with the operating frequency of the instrument, because this megahertz is nothing but operating frequency of the instrument, okay, operating frequency of the instrument, right? So I think these questions have been asked in CSIR. They have given you the values, okay, values to chemical shift values. So first of all, you have to subtract these two. So you will get the value in ppm, and you have to change it in hertz, because the standard unit for coupling constant is hertz. Hence you have to convert it, okay. See, for example, in this case we have got 0.2 ppm, right? Suppose in the question they have given you like the operating frequency of the instrument is 600 megahertz, okay, 600 megahertz. What you have to do? Hertz is equal to ppm, the value in ppm into megahertz, right? So 600 into 2 into 10 power minus 1, right? So 600 into 2, it is 1200 into 10 power minus 1, which is equal to 120 hertz, okay. 120 hertz is the value. This is the coupling constant. This is how you have to find out the coupling constant. So if someone is asking you to find out the coupling constant, you have to subtract the values of the chemical shift, and then you will get the value in ppm. You have to cross multiply with that of the operating frequency, okay, operating frequency. So in this case it is 600 megahertz. So you got the value as 0.2, right? Yes, here it is 0.2. You can write it as 2 into 10 power minus 1. So 600 into 2 operating frequency. So this is what you will get, okay. This is how you have to find out the coupling constant. In this case, the coupling constant J is equal to 120 hertz, okay, 120 hertz. Then we can see the various values of coupling constant for different compounds, okay. Okay, now see here, these are all three compounds, okay. In the first case, what happens is the value is 7 to 8 hertz. Here it is 1 to 3 hertz. Here it is 0 to 1 hertz, okay. So why this value decreases? See here, in this case HA and HP are present at the ortho position. They can couple to a greater extent, right? See here, the number of intervening bonds between these two is 1, 2, 3. Okay, it is J3 coupling. So in this case, this is meta coupling. The number of intervening bonds is 1, 2, 3, 4. Okay, it is known as J4 coupling. And in this case, 1, 2, 3, 4, 5. Okay, it is J5 coupling, right? This is ortho, this is meta, and this is para. Okay, so distance is increasing between these two HA and HP in all these cases. At first it is present between ortho, right? It is present in the ortho position. Here it is in meta position, and here it is in para position. So the distance between them will be maximum in case of para position, and hence they can't couple. Okay, they can't couple to a greater extent. But in this case, this is present in the ortho position, it can couple easily. As a result, the coupling constant value is greater for this, okay, greater for this 7 to 8 hertz. Here it is 1 to 3 hertz, and here in this case it is only 0 to 1 hertz. Okay. So, if you can't keep this in your mind, no problem. Okay, no need to memorize these coupling constant values, J values and all. Because if you know the concept that the electron withdrawing group present means it will be de-shielded. If there is an electron donating group, it will be shielded. If you know these concepts and all, you can easily elucidate the structure. No need to mug up these values, okay, these coupling constant values. But a very important value that you should keep in your mind is this, okay. This is very important. You can easily find out that whether the given compound is cis or trans, okay. If you have double bond, always cis-trans isomerism is possible, right? If the two groups are present on the same side, it is known as cis. If two groups are present on the opposite sides, then it is known as trans, right? So in this case, the the two protons are present on the same side. Hence it is known as cis. In this case, they are present on the opposite sides, and hence it is known as trans, right? Cis-trans isomerism, cis-trans isomerism. Okay, this is known as cis-trans isomerism. See here, it is 10 to 12 hertz for the cis, and it is 16 to 18 hertz for trans. The coupling constant value for trans will be high. Okay, so if you see the value 16 hertz, then obviously the double bond will be in trans position. Okay, this value is very important. You have to keep this in your mind. Only cis-trans. The coupling constant for cis-trans isomerism is very simple. If you have higher value like 16 to 18, then that value will be corresponding to trans position. Okay, trans position. But if you have 10 to 12, it is cis. Okay, so what's the overall review here? See, if there is an ortho para meta compound, then for para the value will be very low, right? Coupling constant value will be very low because the separation between these two is high, right? HA and HP. The number of bonds is greater. The distance is very large in case of this para. Hence, these two cannot couple. Okay. Hence, it will have a lower value. But in case of ortho position, these two groups are present very nearer. Like if it is having only 3 intervening bonds, hence it can couple to a greater extent. It will have higher value. Okay, this is the ortho para meta position. Okay, then in this case cis and trans will have higher value of around 16 to 18 hertz, and here it will have only 10 to 12 hertz. Okay, so if you see the value 16, then you can easily predict that the given compound is trans alkene. Okay, trans alkene. So that's all about this coupling constant. Now I will give you a previous year question. Okay, I will give you a previous year question. You have to find out the answer and comment it in the comment section. Okay, so very simple question I am going to give you. Okay, the question is, in the 400 megahertz proton NMR spectrum of organic compound exhibited a doublet. Okay, so 400 megahertz is the operating frequency of the instrument, right? Once again, I am repeating the question. In the 400 megahertz proton NMR spectrum of organic compound exhibited a doublet. Okay, the two lines of the doublet are delta is equal to 2.35 and delta is equal to 2.38 ppm. Okay, so delta is 2.35 and 2.38. What will be the coupling constant? Okay, what is the coupling constant? So you have to find out and comment your answer in the comment section, right? Very simple, right? Operating frequency is 400 hertz and it is given that delta value is one is 2.35, another one is 2.38. So what is the coupling constant? You just try to share your answer. Okay, I hope this video will be helpful for you. If you find this video helpful, then kindly share with your friends. Okay, stay tuned. Thank you so much for watching.